Thanks, everyone. Thanks for coming. I'm sorry if you can't get a seat. If you have some free seats next to you, just be nice, raise your hand so that actually folks can find it. Today we're going to talk a little bit about resiliency, and especially about complex systems. When you talk about complex systems, very often people have this kind of diagrams in mind. We saw it again this morning in the keynote, right? With kind of the constellations of microservices. There is the one from Amazon, actually, circa 2004, so that's quite a long time ago. We probably added about 1,000 microservices by now. Then there's Twitter, Netflix. But actually, complex systems don't have to be that crazy. If you give a human, for example, 5 or 6 systems put together and try to understand how things work, probably 99% of the time we'll get it wrong. Unless you have a really, really good architect experience with these 10 particular systems for the last 20 years, you might figuring out how they interact with each other or how they might interact with each other. So basically, when you think about complex system, let's say 5, 6, 7 microservices together can already be defined as complex systems. So when you talk about complex systems, you have to deal with something what we call partial failure mode. And actually, this is a video of partial failure mode in action. Basically, the guy is a taxi in India, keeps going, changes the wheel while driving, and that's exactly what it is. And it makes total sense, right? Partial failure mode is actually exactly the mode of operation of most of the systems out there. Because when you have hundreds of microservices working together, you can't at any given time have all of them working. Right? It's just impossible. Statistically, it's impossible to have everything working at the same time. So you can't have a full operational system. So you always run in what we call partial failure mode. And that's exactly what resiliency is all about. Resiliency is about juggling with this kind of failures. How do you recover from it? How do you handle these eventual mistakes that most of the times you can't actually predict? A mistake can come from anywhere. In the last 15 years where I work with complex systems, I've seen squirrels taking down data centers, sharks eating underwater cables, taking entire regions down. I've seen drunk drivers hitting electric cables. So nothing software related, right? And yet we expect software to work all the time. So we have to work with this resiliency in mind. So it's very, very important that we talk about resiliency and that we learn how to build this. And that's exactly what's the topic of this talk. And actually, this talk wouldn't have been made possible without some of the top engineers at AWS. Actually, this talk is a collection of my last 15 years of experience working with large-scale systems, failures, most of the time failures, and trying to recover from them. And some of the things we actually do at Amazon, as well, or AWS, to deploy services in the cloud. They're actually services that are used by millions of customers. So first of all, you will see a collection of patterns, but those patterns are nothing if you don't have the right habits. And actually, I always say it's great to have the best software, the best codes, the best patterns, but if you don't have the right habits of testing, of having the right culture, writing, pushing in production, maintaining, fixing it, usually it doesn't help, right? So I'm just going to give these patterns. Don't expect magic. Right, you have to do the job. You have to implement what we call the jam around all that stuff, right? What makes the culture the right fit for those patterns. So let's deep dive into some of those. And actually, the first pattern is really a regional pattern. And you might have heard that we launched a new region in Stockholm last year. It's actually local to Stockholm, so they are what we call big regions with several AZs, and I'll deep dive into some of those. But the first thing I want to say is actually the excavation and all the rocks that was taken from the data centers have grown a slope to. So if you want to do skis in Estuna, the 10 meters, the last 10 meters of the hills are actually powered by AWS, basically rock as a service. So pretty cool. So this region is actually interesting, and I want to go a little bit in mathematics to explain to you how a region works. If you take a system, let's say comprised of two parts, and part X has an availability of 99%. Just 99% is terrible, right? Because it means that you would have about 3 days, 15 minutes out of outage per year, right? If you have a customer and you say, well, my software is going to be probably down 3 days a year, it's not going to end up well. So the standard is in the industry is usually 4.9, 5.9, right? But if you take a system 99% available and you just put it in parallel, mathematically, it will increase the availability to 4 nines. And that's before you've done anything else, right? So you just take a part, put it in parallel, and you increase your availability. Actually, this is what is happening in most nuclear power plants. They actually put systems 4 or 5 times in parallel simply to avoid having Chernobyl type of events, right? So we can do the same thing with software, and actually, this is actually the way we build regions. Our regions are built using this, what we call availability zone system. So a region has, nowadays, 3 or more AZs. Usually new regions have 3 AZs. An AZ is a collection of data centers. And those data centers can be 1 or more of them within 1 AZ. And the interesting thing with AZ is actually they're fault tolerant. What I mean by that is they are physically separated one another, right? They are a few kilometers apart, usually a different power grid, a different floodplain, a different earthquake plane, so that in case of a major problem or event, any of those AZ will not all have problems at the same time. They will be independent one another. But they're not too far apart so that we can't do synchronous replication. In fact, they are 1 or 2 milliseconds latency separated, right? So that's why in Stockholm we had data centers in 3 different locations. Those are AZs, right? And eventually those AZ might grow as the region will grow. So that's actually the first thing we do. Then we connect those AZs with high throughput private fibers so that we can do synchronous replication. So that means we can build then regional services like S3, DynamoDB, or some of the Kinesis streams, all this kind of stuff, where by default, they'll take the data and actually synchronously replicate it across several of those AZs. Right? So that means our data, or the data that you put in the region, is automatically durable and fault tolerant. In fact, that's how S3 does this 11.9 of durability as well. So we have those AZs, and the first patterns I want to talk about is these patterns of multi-AZ. In fact, we do 2 things. We always recommend customers to do these multi-AZ architectures, but it's actually a patterns we use extensively for building our services that you use, right? Like DynamoDB, S3s, they all have this kind of architectures. And what it means is you simply take a load balancer and distribute the load or the traffic across 3 AZs, where you have an application that can take the load. Now, there's some constraint in the application because most of the time, a load balancer will just do round robin, so move requests without understanding the previous request. So you can hit any of those AZs right, at any given time. So you should never have local state. You should always distribute the state of your application to a cache or to in-memory, distribute in-memory data store, so Elastic Cache, Redis, all this kind of stuff. But actually, it's super easy already with this kind of patterns to achieve high level of availability. In that case, what is interesting is if I have one AZ going down, I have the database that automatically detects that the AZ is going down and will do an automatic failover to the standby instance in the other region so that my application actually will stop sending traffic to the AZ that it's damaged and will move all the traffic to the other healthy zone. So that actually gives you a very high available patterns and enable fault-tolerant application. And it's really a pattern that we leverage all over the place for our own services, right? And it's something that you can do. Now it's not enough for our services because we have millions of users. At peak time, the DynamoDB, for example, at prime days, go easily at 14 million requests per second. So we have to handle this kind of crazy amount of traffic. Especially, we have to have a bit more resistant to blast radius, because in that case, I have 3 AZs, so that means I have 33% roughly of my customers that will be affected by an outage, right? Of case of an AZ outage. So that's probably not enough. So we went to look into how we build boats, actually. And boats have done something very common for the past hundreds of years, is they've built compartments inside the boat so that if the boat hits an iceberg, well, you know the story, the water will progressively go from one compartment to another, right? Ideally, it never goes to the other compartment so that the boat can go forward, right? So there's an interesting idea there. And it's the idea of what we call cell architecture, right? And so if we take the application that I just showed, a multi-AZ application, and we kind of simplify this, we put this in what we call a cell, right? And actually, we take that design and we replicate that across multiple AZs. So that means that we actually have an easy router, a cell router, which is very, very thin layer to route traffic to different cells. And what we do is we replicate this. So that means our regional services become kind of divided as well in cells. So that means our blast radius for regional services like S3, for example, is now reduced. So that means if an AZ go down, I'll be able to recover. But the most important thing in this is for local services like an instance, EBS volumes or things like this, we can have actually within one AZ compartments. So that means we have isolations against AZ failures that helps reduce our blast radius. So the very interesting thing here, and we use that, maybe we can have thousands of cells within one region, right? It's not just 2 or 3. Actually, some of the service has tens of thousands of cells. The very interesting feature here is that we can have workload isolation. And that means that we can have actually rollouts of some of the upgrades we want to do. We can try things in isolation without affecting the other cells, because each cell has its own database. Each cell is unique, is isolated from the other, so it doesn't. The blast radius is limited to one cell if something happens in that cell, right? The interesting thing again here is that actually, in case of failure, my other cells are still working, right? But it's not the only thing. It's like we can scale out. And this is very important because when you have thousands or tens of thousands or hundreds of thousands of customers, you don't want to spread them across 3 AZs only, because that means a blast radius of 33%. So what we do is we create actually tiny cells where we put maybe thousands of tens of thousands of customer maximum, and that limits the blast radius enormously, right? So we actually build cells that are have a maximum number of users, and within that cells we can then do extensive testing, extensive tests with latency, with failure injection. I'll talk about some of those later, but especially how the system handles at max requests per second and concurrent users. So that means we can build a very good image of our systems within one cell and then take that knowledge from one cell and replicate it across all the other cells. So we don't have to build an overall view of how the system behaves with hundreds of millions of users, but more with few thousands. And that's a very good way for us to test our systems as well, and actually to manage. But actually, that's not enough. If you take, for example, a service, and you have a set of, let's say, 8 different customers, and they do requests. Say that one of these customers actually makes a request, one of these requests that are problematic, the intensive request, the 1 in 100 request that can create a problem. Let's say that at this particular time of the day, that request was so extensive or so expensive that it actually starts to take down one of the instances. Of course, that user, most of the time, implements retry. So that means it will start retrying with the same request. That same request that actually took down a server, and then eventually will take all the servers within this cluster. And this is actually quite a problem, and it happens very regularly in a system where you don't compartment. That's exactly what cascading failure is, actually. This is how you can visualize cascading failure. The mom is the load balancer. She has two applications. One goes down. All the traffic goes to the other and takes down the other kid. This is exactly what overload is, right? So if you have two servers that take the load 60% on 60%, and you all of a sudden move 16% over 60%, 120%, that means your server go down. That's overload. That's a classical that's a classical cascading failure. You see this all over the place. Right? So for us, having a lot of different sales actually allow us to mitigate this kind of big cascading failure first. But with cell-based architectures, you limit that, right? So that means our same customer, which sends a kind of a demanding request, in that case, affects only that particular cell in which it was assigned. So if you look at the blast radius, in that case, we move from 100% to 25%, which is quite a big, it's a big win, right, for us. So that means, in that case, we're pretty good. But actually, that's still not enough. You can go into what we call shuffle sharding. And this is something that we started to implement a few years ago, and actually really, really, really good results. So let's take an example of with the same customers. So we have 8 customers. What we do is we randomly or semi-randomly assign them 2 different instances within a cluster. And then we take another customer, assign them 2 random instances different from the others, right? So that means we try not to have overlaps, never the same instance, so we don't have the same customers twice on the same instance, right? So when you do this, actually, you start to realize there's a pattern here that if I have an expensive request and my client customer with his expensive request does a retry, what it does is it does take 2 instances down, but the customers that were affected by here, like the club and heart, now can do retry and will affect another, and will hit another server, which actually will give them resiliency, right? So we have here now fault tolerance simply by doing a retry after a failed operation. And this is very, very good for us for 2 things. First, it really, really reduces our blast radius. So the blast radius, in that case, if you have 8 nodes and 2 shards, you have about 28 different combinations. That gives you actually an overlap of 2, and that gives you 3.6% of blast radius, which is 100%, 25, 3.6. That's only if you have 8 customers and 2 shards, right? Now, if you take, and this is the mathematical equation if you're interested, if you take hundreds of nodes, this is where it becomes interesting. Because now you have 75 million of combinations in which you can assign customers to. That gives you, with an overlap of 5, almost significant blast radius, insignificant blast radius. So this is a pattern that is very, very interesting. And you don't have to be AWS or Amazon to implement similar kind of stuff. Actually, you can implement shuffle sharding using DNS, right? So you make a request to your server through DNS. Your DNS kind of queries, returns you an hash that assigns you a particular set of instance or a cluster. And then you do client affinity to those servers, right? So that means you can do this kind of shuffle sharding. And this is very good pattern. Math at work, nothing much I can say about this. The only thing that is required from the client side is simply having a retry. Right? If you don't do the retry, then you will have a failed operation. That's it. And now this is a pattern actually that is very interesting because it also works for all the other type of systems, like a queue or streaming services, all this kind of stuff, right? Resources that you might need for your systems. Now there's another thing. You probably, if you use AWS, we launched about 8 years ago, a system called Autoscaling. Autoscaling is very nice. You know, the more resource you throw at the system, the system will automatically scale up and down the system. So this is nice. But actually, this is not what is very interesting here. What the most interesting thing with autoscaling is what we call self-healing, right? And that's inherent to the configuration, how the system is built. If you give to the auto configuration, the auto-scaling configuration, a minimum instance that is higher than 0, the system will automatically always regenerate one instance from what we call a golden AMI, right? The immutable infrastructure type of patterns. So you have a golden AMI, which you set as a basic for your auto-scaling group, and that auto-scaling group, if it sees a mistake, like for example, if one of the instances fails, the system takes it down and automatically starts a new one without you having to do anything. And this is literally within minutes. So the load balancer will take out the instance, shift the traffic to the other instance, the new instance starts, and as soon as the new instance is healthy, we'll send back traffic to this. And this is super, super easy self-healing pattern. And I would say it's much better to use these kind of things than very complicated systems. This is how you'd see at work. So for example, here I have 2 dashboards. I have an auto-scaling group on the left, which has an instance running in it. It's in service currently. I take the instance, I terminate it. So you see at the end up there is going to go shutting. Then it's terminated. And the system automatically detects that the instance is terminated, and now will or see that the system is unhealthy, and will launch a new one automatically. And this is really easy pattern. The 5th pattern I want to talk about is about asynchronicity, right? You all know asynchronous versus asynchronous. I'm not going to talk too much about it. It's quite obvious. Now, what is interesting with this is when you start decoupling your application, right? Especially what we notice is that the API front end, or on the backend side, the API receiving end is usually bound to something different than what the working instances are. So very often people will write an application that takes an API, process that, and then answer it. Now, the problem with this is your API are most of the time memory or CPU bound at the beginning and tend to be memory bound at the end when you start to have a lot of concurrent users. So that means you have a hard time to do efficient scaling or planning or all this kind of stuff. Now, what you can do is actually decouple the API receiving part of your application to the worker instance and using queues. And this is a beautiful pattern to decouple both systems. So for example, in that case, I have an API that launched to do something, a foo, a task. I get this, assign a job ID, put it in a queue, and then return immediately. Now, of course, you might say, yeah, right, but if I design application and I return immediately without the result, how do I build applications like this? Well, that's exactly the art of managing asynchronous system. And very often, it's something you need to start from the beginning, right? You need to start from the UI down to the very low parts of the system. Because if you start to have one part that is asynchronous and the rest is synchronous, it just makes no sense. So you're going to have, a UI that's going to have spinning icons until the video is uploaded that blocks everything behind. So these kind of patterns are good for non-blocking UIs, which start to become very popular. In fact, if you use Instagram, Facebook, all those applications that are very widely distributed, they already do that. They take the task, push it up there in the queue, and then you can continue using your application. And if the upload or the task fails behind, they will start retrying until it's completed. So you put this job, you put it in the queue, then you have your worker instances that take that and actually put the results in cache, and then you can send notification to your end user that, hey, my job is finished, come and fetch the results. And now you might think, okay, that actually will take a lot of time, but actually what I've seen in production with large scale, with many, many millions of users, the differences is very, very minimal. Very often, the task will be sent, fixed as fast as possible. Now, the good thing with this is you can do what we call, but first, you can actually scale the API part and the working part. If one is CPU or memory bound, then you can have auto-scaling groups for the workers. You can divide the workers by groups. Some of the tasks might be very CPU bound, so you can then optimize for that. Some might be memory bound, some might be concurrent user, a number of concurrent user bound, all this kind of stuff. So you can start to optimize, and this is a very good way to do it. But the most interesting with this kind of decoupling is actually you can, in case of failures, you can start do deep prioritization. So that means if you have an idea of what are the critical API within your systems, the APIs that you really, really want your client to have, even in case of partial failure, then you can do degradation. So that means you can take an API and say, oh, this is not really relevant. I'll put it in the maybe when I can queue. Oh, this is a very urgent API. I'll actually assign most of the resource to it. I'll put it in a high priority queue. Most of the workers will be assigned to it. So that means you can do what we call partial degradations, simply using this kind of prioritization. And this is a beautiful pattern if you implement this from very early on, right? Because you need to have an idea of what are your critical APIs. You need to have some sort of understanding between the backend and the clients on what to do with these APIs and how to prioritize them. But this is very, very nice. Now let's talk a little bit about timeouts and retry. I know we had a bit of a talk this morning about this. I want to give a very simple example, which I've seen taking systems down very, very regularly. A client makes an API call to a backend. The backend calls a database. That database, at some point, will eventually start to slow down. Right? It happens all the time. Database eventually will slow down. Depends on the number of concurrent users you have, depend on the memory, depend on the configuration or the mistakes you've done on the configurations. It eventually will happen that, hey, what's happening? My database is slowing down. So let's take a request here. What happens if my database goes down? So I have maybe thought about, okay, my client-side timeouts and maybe the backend-side timeouts. But let's say I use what we call a default. Very often on the client side, it might be 10 seconds, and on the backend side, we don't really know. It really depends. But let's take this query, for example. My user makes a request to the application. The application makes an insert into the database. The database doesn't go down, slows down. My API slows down, right? It doesn't, the backend or the database doesn't say, okay. So what happens actually here? Well, imagine I have a client-side timeout. Well, after 10 seconds, my client will say, I need to time out. But we had also a timeout on the backend, right? So what happens if my backend timeout is, let's say, default, and which is very often -1 or infinite or not implemented or 60 seconds or 50 minutes. Very often you have a break in there. So you mean my database connection stays up, but the client times out. So the client does a retry, right? And same stuff happens. You make a request. The database is still slowing down. The request doesn't terminate. Goes back. My timeout is passed. Client stops, does a retry. And before you know it, you've seen that. How many of you have seen that? Fail to get connection pull. It's very, very classic. And this is actually most of the time the reason why it happens. You have exhausted all the resources, you haven't closed the database connections, or you have some queries which are locking a database and accumulate in the queue, and your database starts to reject. Welcome, update queries. And that's a big problem. Actually, and if you look at Python implementation, this is Python. And here implementation is actually, on the top is infinite timeout. The second one is Tomcat as well, or servlet. This is 30 minutes. And then Tomcat at the end, 30 minutes. Why? Why? And actually, every time we do customer outage analysis, 90% of the time, it's a timeout issue, right? So what do you want to do with this? Well, and actually, this is database as well. I even prefer, I love when database have timeouts of infinite. So basically, they never ever timeout. This is, in my opinion, crazy. So rule number one, always, always implement your timeout. But that's not it, right? Because now we had the problem. We had the client timeout, then the backend timeout. What happens if you have like 4 or 5 systems? Where do you implement timeouts? Do you make timeouts at every level? Well, you can. Most of the time, you will fail miserably, or you'll be able to document your timeout for the first 3 weeks, and then someone will make a change, forget to update the documentation, and that will end up in a similar outage. So what we start to want to do or do is actually pass the timeout from the client and have it as an inherit, so that all the subsequent, let's say, requests coming from this client will inherit the initial timeout and actually will know how much timeout is left as well for its query. So then you can set the right timeout, right? You don't have to fix your timeout all the time. You can make it dynamic. And it's actually very interesting to have it dynamic because in case of an outage and you try to recover, most of the time the system will be a lot slower. And you don't want to have to go and fix your configuration live in the system. Oh, my timeout is only 5 seconds. I need to increase it to 10 seconds. Let me log in the servers. That's not. So you want that to be as dynamic as possible, adaptive, right, to the condition of the network. So think about it. Have the client maybe pass the timeout, but it's not all, right? The client needs to have an understanding of what's the overall health of the application. So how else could we have prevented actually this kind of issue? Anyone wants to give a shot? There's a very simple way to avoid this kind of... What's that? Very well. So before I go into circuit breaker, actually most of circuit breaker implement that, so that's why it's good. You could simply do what we call exponential backoff or backing off. So, you know, my client was doing a retry, right? Every failed request, the client did immediate retry, big mistake. If you have hundreds of thousands of clients, all at the same time retrying, immediately all the time after failed request is the best way to see massive outages, right? So what you want to do is, okay, my request failed, then you want to back off. So that means you want to wait, maybe first 2 seconds before retrying. If it doesn't work, 4, 8, 6. So that's called exponential backoff. But actually, that's not enough. So we did some, so the backoff will basically start to free up requests after 10 seconds, right? Because that's when I start having the benefit of it. But we did some research actually, and there's a whole paper you can read, and there's a code available on GitHub as well on backing off. And what we notice is if you simply back off, it's not enough. You will still, as shown in this diagram, you will still create clusters of retry. So even in very large-scale systems, eventually all retry will be grouped together. And that's enough to not being able to recover from outage or actually to do resource exhaustion. So what we notice is the best way to do that is actually to add jitter. So you do an exponential backoff plus randomly add jitter in your expression. So that looks something like this. First sleep is an exponential backoff, and then you randomly add jitter inside the second equation. And what it does is removes part of the work from all the clients. So basically, your clients can start retrying with a lot less work and do a lot more and faster. Right? So basically, that's very, very good. So you see the first curve up there is with none. So basically, you do a lot of work and very intensively for the clients versus having a full jitter or equal jitter type of implementation. It's written in the paper. You can go deeper if you want. It's very interesting, by the way. You can actually remove a lot of the work on the client. And this is very, very good. So that means when you implement microservices, clients, or anything, always, always verify that actually first there is exponential backoff, because very often there's none. It's usually immediate retry. Even in 2019, that should never be like this. You should always back off. And then if you want to further optimize it, do jitter injection. And this is how it would look like in Python. But since it's a Java conference, I'm not going to show into that. That might reduce, or I might be shot. You never know. Now, when you do retries, there's something super important to do. Because in a complex systems, you might do retries, but you never really, really know if your retry has completed before timing out. So that means you need to make sure your requests are idempotent. So that means your requests always, always do the same thing, regardless if they execute or not. And that can be a problem. That means that you need to track or hash a request and figure out has this been executed, and figure out if it has, what should I do? Should I just cancel it, or should I go back to the client? There's nothing much here that I can give you tips. It's really, really depend on the application, depend on if it's necessary, but it's something that you need to be aware. If you have retries, do make sure that they are independent. You don't want to end up with 100 retries that put, let's say, my address is Stockholm 100 times in the database for 1,000 millions of customers. That's the best way to jam your database and kill it and regret it. Now there's something that is important, because our client needs somehow to understand what's going on in the application. So you need to probe for health. And there's a problem, right? Because in that case, this is an application that can push data to a cluster to do some calculation, send some email, put data into a database, or put something in cache. But there's a problem here. The problem is, well, what is critical and what is not? So there's two ways you can actually figuring out the health of your environment, is doing a shallow health check. A shallow health check will simply check maybe even the load balancer or the first instance of your application, say, oh, are you healthy? This is good, I'm fine, it's all good. But the problem with shallow health check is if I have an email server here, if I have an email server that is experiencing issue, my shallow health check will still say, hey, yeah, I'm all good, send me traffic. And that can be a problem, right? You have deep health check, right? The deep health check will go a little bit further. That means it will query all the subsequent services and ask for their health. If all of them return healthy, then you return healthy. But if only one of them returns unhealthy, then the whole thing will be unhealthy. And this is a big problem again, because my email maybe is not critical. I don't have to send email right away, So when you design system for health, the first thing you need to do is an understanding of each API, which are the critical services that you need for that API. And then have quite complex maybe health check, figuring out for each API which are those services that actually are working, which are not, how you can maybe take them off from the health check. What we notice is actually you have to have a combination of both health checks. And both health checks are very interesting to work together because, for example, if you have an outage and you try to recover from it, very often your system will be a bit slower. You might have system down the request path that actually not necessarily yet up. So for example, my cluster might take 10 minutes to start up, but everything else is still fine, can receive traffic. Should you say, no, I'm not ready, don't send me, my cluster is not ready, don't send me traffic, or should you just use a queue to deprioritize that API still have a health check returning, okay, send me traffic. I'm in degraded state, but send me traffic. I can't do this for the moment, and then eventually we'll recover. And this is exactly why it's important. Again, it's important to think about it. There's no perfect answer here. It depends on the application, depends on the APIs you do, it depends on the criticality of your services, but I have an understanding of both and how each of the APIs might use your downstream services and figuring out how you can return this to the client to make the client a little bit smarter. And in fact, this is used very often, and this is a very beautiful example of having an understanding of what's happening in the backend. You probably often use Netflix or have used Netflix. Netflix is very good at doing service degradation because their UI is done for that. So they have services which are actually stacked on top of each other. Most of those are my list, top trending, recommended because you watch Jason Bourne, recommended because you love Titanic, or this kind of stuff. All these are microservices that feeds information. If any of them fail, it gets back to the client. The client notices that the service is not there, and stack up, simply removes it. And this is a beautiful way to do that. But that takes me to the pattern number 8, which was mentioned, is actually when you have all this information, it's very, very important to do what we call pattern secret breaker. Secret breaker isolates kind of services from one another, or take a request and put it in an object, and that object will monitor the health of the object that it wants to talk to. And if they are past a threshold, if the system is not available, will trigger and break and then do a fallback. Now, the beautiful thing with that is actually not necessarily the circuit breaker itself, is actually it forces developers to think about the degradation, because that object, when you initialize it in your code, you need to give it a fallback. So that makes you think about it, and very often fixes 90% of the issues. Right. So if you are into circuit breakers, there's a very nice implementation of Netflix, from Netflix called Asterix, which does that beautifully, that you can use. Now, if you think about databases, it's also a big problem, and there's few ways you can scale databases and make them resilient. The first one is actually do what we call database federation. Very often I see people putting tables in the same database, tables that have no relation, and then if one experiences an issue, or if they need to make a fix into one, or change the schema into one, affects everything else, and then it leads to actually have teams of developers never ever touch the database because everyone is scared of touching the database, is often left the last thing to worry about is, oh, I don't want to touch that. Everything else is super beautiful. The database is like, well, hopefully it works. So federation is quite easy. We've done that at Amazon in the early 2000s. We did an analysis of our requests, and we noticed that actually 70% of the requests to the database were not transactional. And guess what? We were using 100% transactional databases. Well, that's a big problem, right? Because that means we're not using the system for what they're good at. So that's why we moved to NoSQL effort with DynamoDB and all that kind of stuff. So federation is something which is easy. Sharding is also something easy. So in that case, for us in sales, when we assign customers in sales, we all do also sharding based on the sale ID or on the geography of that users, all this kind of stuff. So that means we are able to then have a smaller blast radius for that database. And instead of trying to do live analytics on production database, actually we replicate data to a data lake, and on which we do analytics. We try never ever to do reports on production database. Instead, we copy or move the data apart, right? So sharding is very easy and gives you a very good way of kind of building resiliency inside your cells. But the most interesting here is actually read-write separation. So this is a super no-brainer, super easy to do, especially most of the database drivers now supports these kind of things. So you have a database in which you have a master and then read replicas, and you send write operation to the masters and all the reads to the read replicas. Of course, you need to be aware of the cap theorem, that you might have a lag of replication between the master and the read replica. But hey, we are asynchronous, it's OK. And we build with this in mind. So when you do that, you can do degradation. And guess what? You can go into read-only mode. And that's actually a beautiful pattern. Say, for example, Prime Video. Business is to deliver video. It's not to write in a database. So when we have issue on the database, we move into read-only mode. We don't store anything in the database, but you can still consume videos. Actually, it sounds very simple, but most of the applications that I've seen in production back in the days never, ever supported read-only mode. How many of you support read-only mode nowadays? Oh, there's 3 hands, right? Exactly. Is your business to write in database? Probably not. You can do in queue, you can do offloading, you can do store the data in memory, and then once the database is back up, you actually can go back there. So this is a beautiful pattern. You have to use it. And the 9 plus is do not use database to store mutable data. Like if you have a counter, don't put it in database. If you have something that you have to update after 10 seconds or 20 seconds, do not put this in database. Use Redis, use Memcache, use any other in-memory data stores. They are great for that. If you have lists, reverse sets, Redis, amazing for that. Do not eat your database credits with that kind of stuff. One of the biggest outages I've had is because we've done a problem and I'd written an update query on the to store counters in our database. Literally took 160 servers down in 23 minutes. Never do that. That was not AWS service. It was a company which went bankrupt. The last one is that one. In the early 2000s, we hired a guy called Jesse Robbins. Jesse Robbins is a firefighter. He came with a background that actually 80% of his time was as a firefighter, fighting or learning how to fight fire, and 20% of the time deployed in a real fire situation. And they do this to build intuition. And actually, we can do this the same, software developers. Right? When there's an outage, very often we're not prepared. Very often our heart rate goes high, we start sweating, we start like, not me. It's at 1 a.m. in the evening, it's Friday and it's Sunday. Usually that's actually 80% of the outage I've had is either Christmas, birthdays, or weddings, right? And you don't want that. So what we did, we hired Jesse Robbins, and Jesse Robbins started something called Game Days. He would just randomly walk into a data center, pull out cables, and see if we could recover. And actually, really, what we were doing, he even took a whole data center down once, never did it again. But this is the kind of stuff that we started to do, and we still do to date, right? We actually, most people know that as chaos engineering, and we still do chaos engineering very, very often in production. We break things trying to figure out if actually our assumptions of or if our hypothesis of how the system might react or recover is actually true. Right? And this is very important. At large scale, you cannot only test in a dev environment. You actually have to find a way to test in production environment. And for that, it's super, super interesting to have this kind of sales or have shuffle sharding, because then you limit the blast radius in which you can actually start testing, right? You might have unlucky customers that, hey, yeah, you were a victim of a chaos engineering attempt, but if you're smart, you actually don't push a payable customer into that and push your mother into this instead. But chaos engineering is something that you have to really to look at. And I know a lot of people are scared about it because chaos sounds scary, but don't call it chaos engineering, call it reliability engineering. This is how we call it inside AWS. It's a lot friendlier. All the team I work with react a lot better when you say, hey, we're going to do some reliability testing instead of, hey, we're going to inject chaos. When you do that, just 1 minute, no? 1 minute. Okay, 30 seconds. 40 seconds. When you do that, you need to know the steady states. And this morning, there was a very good remark in the keynote that says, hey, what is the steady state? Should not be CPU, should not be memory. Netflix, they have the number of times you play button worldwide. At AWS, we track the number of number of orders per second. And if we see a problem, we can say, hey, there might be a problem in the systems, right? Always have metrics which are actually customer focused and not, customer CPU focused. And then play with injections from all the way from your application down to what we call the pole attack. Is the guy who does everything. Just take him down, don't bring his laptop, and let him go home without having him to do anything at work. And you'll see system will fail. So it's a very good way to start implementing resiliency. Last thing, plan for the worst, prepare for the unexpected, because actually it will be unexpected when things fail. Thanks very much. If you want to read more, I have a whole stuff on Medium.